ॐ सहनाववतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः।
In the last class, we started our discussion on strain energy density and strain energy density function. We said that for elastic materials, it is important that a function called strain energy density function exists. Or in other words, we postulate the existence of a function called strain energy density function. We also said that the relationship between stress and strain is given by means of an equation of the form sigma ij is equal to dou w by dou epsilon ij, right. That is what we said. Now, what does it mean? It means that if you are able to define a strain energy density function, okay, how do you define it? Looking at the behavior of the material and so on, then the stress strain relationship is obtained from this equation. For example, if you look at an elastic material, I can define a strain energy density function to be half of C ij KL epsilon ij epsilon KL. The definition of strain energy density function, this say for example definition of this function is quite involved. Okay, there are a lot of things that you have to satisfy, but I am not going into the details of it, how I got this, because that is a separate course altogether. But nevertheless, satisfying some very fundamental criteria which are based on thermodynamics and so on, it is possible to write down, it is possible to write down for a class of material, okay, functions. For example, this is the function for a linear elastic material. Okay. Similar functions can be written down, for example, for a elastomer or rubber and so on. And in fact, you can look at a material to be distinguished by means of this kind of strain energy density function. Okay. These materials which are defined by means of this root are called as green elastic material. They are thermodynamically very correct, mechanics wise, or rather more broadly continuum mechanics wise, they are well defined materials. If I, for example, if I define W is equal to C ij KL epsilon ij epsilon KL, then I can write down my stress strain relationship to be sigma ij, that is dou W by dou epsilon ij, which you can just expand it and write it. I will get C ij KL epsilon KL, C ij KL epsilon KL. Okay. Now, in other words, what is this? A second order tensor, a second order tensor being transformed by a fourth order tensor. So, in other words, a fourth order tensor is a transformation function. Okay. I am not going to work out this step, I think by now you should be familiar with this, you can work it out as well as, I mean, very easily, right. Now, that is actually the what we call as elastic or linear elastic constitutive equation, material which obeys Hooke's law, or a broader, rather I should say that material which is isotropic Hookean material is a subclass of this, rather I should say that they are the elastic or linear elastic materials general equation. Now, the question that immediately comes to your mind is that, look, what have you put C, I, J, K, L, and you have asked us to vary I, J, K and L, each 3 times, 1, 2 and 3. So, I seem to get how much? 81 constants. So, I seem to get 81 constants by doing whatever you have said, but I know only of 2 constants. If I look at steel, I know only 2 constants. So, these 2 constants I am familiar with are Young's modulus and Poisson's ratio. Now, what are you talking about, or how do you connect now this 81 constants to these 2 constants? That is the question that is uppermost in our minds. Is that clear? In order to get from here to here, we have to see what all the assumptions that have gone into defining a material, like for example steel, say for example a connecting rod which we come across. What are the assumptions that have gone in? Okay. This is a very general material, elastic material no doubt, but very general. Okay. Now, what are the assumptions that have gone in to get to these 2 constants? Can someone guess? Isotropic. Okay. Yes. So, isotropic homogeneous material. What do you mean by isotropic material? Yes, properties are same in all directions. Properties are same in all directions. So, however I rotate this, okay, the properties are the same. More clearly, more in a mundane sense, if I have a sheet, okay, if I take a tensile piece from the sheet with whatever be the orientation, I am going to get the same properties. Is that clear? And that is a major assumption. What does this assumption give us? Okay, we get into, or we signify this, or we put this mathematically. See how mathematics now plays into picture. We say that, okay, if you are talking about isotropic material, then I can put a subclass to this 4th order tensor. That subclass of this 4th order tensor is an isotropic tensor. Is an isotropic tensor. Okay. Now, what is an isotropic tensor? Fortunately for us, there is a lot of mathematical effort to define isotropic tensor. So, in fact, a person called Jeffries in 1973, okay, found out that an isotropic tensor of the 4th order, sayCijkl of the 4th order, can be written by means of, or with the help of 3 constants only. Say for example, I can say delta Ij delta Kl plus say eta delta Ik delta Jl plus say nu or beta delta Il delta Jk. Okay. So, he said that if at all there is an isotropic tensor, 4th order tensor, he defined that this isotropic tensor can be written by this fashion. What does it mean? It means that whenever I do a transformation, we have not studied transformation, does not matter, whenever I do transformation of the coordinate system, okay, of the coordinate system, my tensor will not change. That is what is meant by isotropic property. Okay, this 4th order tensor will not change. So, he arrived at mathematically and said that, look, if you are able to write it in this fashion, then this tensor happens to be an isotropic tensor. Is that clear? He looked at each say for example, he looked at second order tensor and said that delta ij is the only second order tensor which is isotropic and so on. Okay, let us not worry about his paper, but it is very important that we realize that this isotropy, the property called isotropy, can be converted into a mathematical form and written like this. Is that clear? Okay. Now let me substitute that equation into this equationCijkl epsilon kl and see what happens. So now this can be written as sigma ij equal to, note this carefully, so you will get some practice in writing down the indical notations. Sigma ij is equal to delta into delta ij delta kl into epsilon kl. What is that I will get? Delta lambda into delta ij delta kl into epsilon kl. Kk, yeah, right, but what happens to delta ij? That remains, correct, that is all. Delta ij k should become equal to L, and so epsilon kl will become kk. Beautiful. So epsilon kk plus eta into delta ik delta jl, eta into delta ik delta jl epsilon kl. So what will happen? K will become I, j will become L. So this will become eta into epsilon ij. Is that clear? Yeah, because jl ik will become, I and k will become the same, and j and L will become the same. So you will see that this becomes eta into, okay, ik jl epsilon kl will become epsilon ij. Is that clear? Okay. What will happen to the last term? Let's hear some answers from you. What will happen to the last term? Beta will remain the same, yeah, of course. Epsilon ji, that's correct. So beta into say epsilon ji, right. Can I? Yes, you are ahead of me, that's very good. So epsilon ij is equal to epsilon ji, symmetry, right. So this equation can be written as delta into lambda into delta ij epsilon kk plus say eta plus beta epsilon ij, right. Now eta and beta, lambda and all are constants. So let me replace this eta plus beta as 2 mu. Let us return, because I just want to write this as 2 mu. There are some advantages of doing it. So let this be 2 mu. So that you can write that equation as lambda plus 2 mu to epsilon ij. Okay, that is sigma ij. Is that clear? Please remember, we are trying to get to the stress strain relationship. Again, just going back, we have strain displacement relationship, right. We had an equilibrium equation. Now we have gone ahead to determine the stress strain relationship. Lambda and mu are called as Lame's constant. They are more fundamental, they are fundamental parameters which come out because of the fact that the material is isotropic. See how we have reduced now, very simple. By just using a mathematical property, when Jeffreys did it, he did not look at steel, but what he did was to look at a fourth order tensor. But then what did we do? We said, oh god, this is isotropy, so I can use an isotropic tensor. So let me pick the property of an isotropic tensor and see what do I get out of it. Apart from that, I also used one more, that epsilon ij is equal to epsilon ji, or in other words epsilon is symmetric, and ultimately I arrive at an equation of the form where the equation defines this relationship between strain and stress by means of just two constants. Is that clear? Lambda and mu are called as Lamè's constant. Okay. Now I know you are still not satisfied, because you have been taught in your earlier classes, very correctly so, that E and nu are the ones we should look for. Lambda and mu are not the ones which strikes a bell. Okay? Sure. So still E and nu. You will also see that, or you would have also heard about shear modulus, bulk modulus, and all that, but all those things still don't ring a bell. It's only E and nu. Let us see whether I can convert these two constants, or can I relate, or can I write first of all lambda and mu in terms of E and nu, or can I exchange these two constants. For that, let me go to my familiar trick of looking at a uniaxial case. Okay, let us look at a uniaxial case. See whether I can derive from a uniaxial case this relationship. How do I write for a uniaxial case? Okay, first of all, I am not very sure you understood this equation. This looks quite complex, but maybe you are more still not so familiar with integral notations. Do you want me to write down that one equation completely so that you will understand what it means? Maybe I think, yeah, right? Yes, you could have asked me that. That's I know that it's important that you understand. So let us say that I'll write it down to sigma 1 1. So I know a lot of people want to avoid integral notation. Okay, in fact, there's a higher or a more simpler way of writing it, but still that also is difficult. Okay, I can write this in a tensorial form. That's also difficult. Okay, so the integral notations are cumbersome to write, but they are they bring down the way you write it. For example, our sigma is equal to c. I can write c epsilon straight away. Okay, that's a tensorial form in which I can write. Some people write it as sigma, okay, double dot epsilon, and so on. This is still contracting the whole thing. The more the lazy we become, the less we write. Okay, but it's not only for that, okay, but also that we can do manipulations much more easily with this kind of forms. Is that clear? Okay. See, we are still like learning integral notations, and it's important that we learn how to write sigma ij. Let me write it for sigma 1 1. So when I write sigma 1 1, what happens to delta ij? That becomes 1, and so I write this as lambda into epsilon kk, and hence epsilon kk can be written as 1 1 plus 2 2. That's a 1 1 2 2 plus 3 3 plus 2 mu into epsilon 1 1. That's it. What happens to sigma 1 2? 2 mu epsilon 1 2. So what do you recognize as this as? 2 mu epsilon 1 2. What is that? What is it that relates sigma 1 2? I know that there is going to be a confusion. What is the problem with us is that we are so familiar with E. What is shear modulus? What is the definition of shear modulus? What is the definition of shear modulus? See, the problem with finite element and other thing is you have to be very clear with definition. Yeah, what is it? Shear stress by shear strain, very good. What is this shear strain? 2 into epsilon 1 2, that means gamma, shear modulus relates gamma. Please note that it is sigma is equal to g gamma. So mu into 2 epsilon 1 2, that means 2 epsilon 1 2 is what? Gamma 1 2, remember last class we did that. So sigma is equal to g gamma, and hence sigma 1 2 is equal to g gamma 1 2. So, and so what is mu? Shear modulus. Okay? Is everyone with me? Okay. Right. So we are now comfortable writing this, and hence let us write down an equation for a uniaxial case. Let us write down for an equation for what happens in the uniaxial case? Let us say that the uniaxial stress is, say, yes, some stress. I just write it, yes. Let us say that epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3, okay, let me call this as sigma. Sorry. Okay, clear? Okay, now write down this equation. So S is equal to, so what is that I have? I have only sigma 1 1 stress. I do not have sigma 2 2 and sigma 3 3. So sigma 1 1, that is S is equal to, how do I write? Lambda sigma plus 2 mu epsilon 1 1. Now what happens to the second equation? Say 2 2 I want to write, 0 is equal to 2 mu epsilon, not 1 2, we are writing 2 2, so epsilon 2 2, okay, and 0 is equal to lambda sigma plus 2 mu epsilon 3 3, right? Let us now sum them up. Sum these three equations, 1 2 and 3. So what is that we get? S is equal to 3 lambda sigma plus 2 mu sigma. So that is equal to, S is equal to sigma into 3 lambda plus 2 mu. Right? Is it clear? Okay. Let me now substitute that equation, okay, into this equation. From that equation, let me write down or substitute it into that equation. Or in other words, for sigma, let me substitute it in the first equation, so that I will get S is equal to, what do I get? Lambda into S divided by 3 lambda plus 2 mu plus 2 mu epsilon 1 1. Right? Now, what is S? How do I write S? What is S? Stress. So in terms of E, what is that we are trying to do? Please don't forget that. We want to shift to E. So I can write this as E into epsilon 1 1. Okay? And here also E into epsilon 1 1. Right? So cancelling epsilon 1 1 throughout, right? Is that clear? Now I can solve for E straight away. So E into 3 lambda plus 2 mu. Okay. I will give you a minute to work it out and look at that equation, work it out and tell me what is the result for E. What is the result? Just look at this equation and 3 is it mu by lambda plus mu or yeah, mu into 3 lambda plus 2 mu divided by lambda plus mu. Beautiful. So we now see that there is a relationship between E and mu and lambda, right? Okay. Now let us now bring into picture nu, because we want to swap lambda and mu with E and nu. Let us bring that into picture. Let us look at the definition of nu. Okay. What is nu? The Poisson's ratio. Lateral, okay, lateral strain to linear strain. Okay. So how do I define that? Say this is defined as minus epsilon 22 by epsilon 11. Okay. Now let me get epsilon 22, say for example from the second equation, this equation, because this is equal to 0. So epsilon 22 is equal to minus lambda sigma divided by 2 mu. Okay. So let me write that down, that is equal to lambda sigma divided by 2 mu into 1 divided by epsilon 11. Okay. Now I know what are the things I know. I know sigma is equal to S divided by 3 lambda plus 2 mu. So this I can write it down as, from here, this just small jugglery, algebraic jugglery, nothing I am doing. S divided by 3 lambda plus 2 mu, right? Now what is S? S is E epsilon 11, epsilon 11, E into epsilon 11. Okay. This and this goes. What is E? E also I have it from there. What is E? So this goes off, mu divided by 3 lambda plus 2 mu, right? From here I am writing, divided by lambda plus mu. Is that clear? So that removing this, removing this, removing this, removing this, mu is equal to lambda divided by 2 into lambda plus mu. Is that clear? So what is that we have done? We see that E and nu can very easily be represented in terms of lambda plus mu, lambda and mu, sorry. Okay. Any questions? So I can now invert the whole thing. I can now write lambda is equal to and mu is equal to in terms of E and nu, right? Let us see what is the result. I am not going to do that algebra again, it's quite a simple algebra. Let us look at how or what is the expression when I now write it by inverting it. Any questions so far? Clear? Okay. So that E, by inverting it, I get E is equal to mu into 3 lambda plus 2 mu divided by lambda plus mu, and mu or nu is equal to sorry, that is what we derived now. Okay, I am just rewriting that, or I think it is not necessary, lambda, Okay, let me write that down. Lambda divided by 2 into lambda plus mu. That's what we derived. Okay, and hence I will write down lambda in terms of nu and E, and lambda is equal to E nu divided by 1 plus nu into 1 minus 2 nu. E nu divided by 1 plus nu into 1 minus 2 nu. This is very important. Okay, this expression, and the next expression that I am going to write, mu is equal to E divided by 2 into 1 minus nu. Okay, so once I know these two expressions, I can now go back and write my sigma ij's in terms of E and nu. Now look at this expression for a minute. What is that? Oh, sorry, mu is equal to lambda plus 1. E is equal to E divided by 2 into 1 plus nu. Okay, what is this? Shear modulus. Maybe you would have used it before, and hence, okay, shear modulus E nu relationship comes out very clearly. Again, you can identify that this expression is for shear modulus. Is that clear? Okay, now let me substitute this simple algebra into my earlier expression for sigma ij. Can you do that, and let's see what you get out of it. Let's write it for sigma 11 so that you don't get confused. Okay, unfortunately I have removed that. So can someone write it for in terms of sigma 11? No, write it in terms of this and tell me. E, so E nu divided by 1 minus 1 nu, or 1 plus nu into 1 minus 2 nu into epsilon 11 plus epsilon 22 plus epsilon 33 plus 2 mu plus E by 1 plus nu into epsilon 11. Right? Okay. So that can be written as sigma 11 is equal to, okay, rearranging the terms, okay, E nu, let me take this out, E nu divided by 1 plus nu into 1 minus 2 nu. Okay, let me take that out. So what happens to the epsilon 11 term? So this will be 1 plus 1 minus 2 nu epsilon 11, right? Plus epsilon 22 plus epsilon 33. Wait. E nu I have taken it out. Okay. Let me not take, so that it is easier. So that this will be nu. Okay. So that will be easier to write. So nu. Is that okay? So that is easier to write. So nu 1 minus 2 nu. Okay. So this becomes, so this fellow becomes, the whole thing becomes 1 minus nu, right, into epsilon 11 plus nu epsilon 22 plus nu epsilon 3 3. Right? Is that clear? I know the expressions are big, but I think it is very easy to derive. There is nothing much, a simple manipulation. How will now sigma 2 2 appear? How will sigma 2 2 appear? No, no, tell me the full expression. Sigma 2 2 is equal to E divided by same thing into 1%, nu into 1 plus, correct, 1 minus nu into epsilon 2 2 plus nu epsilon 3 3. Okay? The same way we are going to get for sigma 3 3 as well. Okay. Now what happens to sigma 1 2? How does the sigma 1 2 term appear? Go back and refer to whatever we have done and tell me. Yeah, right. So let us now put them in a matrix form. Okay, let us now put them in a matrix form to understand the relationship between sigma and epsilon. On one hand, let me write this as sigma 1 1, sigma 2 2, sigma 3 3, 1 2, 1 3 and 3 2. Right? Or sometimes you write it as, so that just to maintain consistency, let me write it as 2 3 and 3 1. So 1 2 2 3 3 1. Right? On the other hand, let me write this strain terms as epsilon 1 1, epsilon 2 2, epsilon 3 3. Note this carefully, the next thing what I am going to write. I am going to write gamma 1 2. Okay, why is that I have written? Traditionally, please note that traditionally many finite element books write not 2 epsilon 1 2 but gamma 1 2. This is very important. Suppose you are going to go and implement a finite element scheme, you have to be careful as to what is the strain you are calculating. If you calculate epsilon 1 2, correspondingly you have to make adjustments in the strain displacement relationship. That 2 you should not forget that 2. That's very important, because traditionally engineers have defined, okay, the strain to be gamma. The mathematicians came and said, look, this gamma is not very convenient, why not you look at it, or why not you put it as 2 epsilon, basically because they wanted to introduce tensorial properties. That's why they did it. But whereas traditionally we have been using gamma, hence usually gamma 1 2 is put there. Okay, gamma 1 2, gamma 2 3 and gamma 3 1. And what is in between the two is the stress strain matrix, which is called sometimes as C matrix or sometimes as D matrix and so on. Okay, there are a lot of things that sometimes people call this as E matrix itself, sometimes people call it as C matrix, sometimes people call it as D matrix. So what is this matrix? E into, there are different ways of writing. So I'm writing it like this: 1 plus nu into 1 minus 2 nu. I'm taking this out. Sorry. One plus nu into 1 minus 2 nu. I am taking this out and then writing a 6 by 6 matrix. But what is it? What is important here? What is it that is important here to realize? Yes. So it is a symmetric matrix, right? Okay. Can you fill this up? Can you fill it up? So what is the first term? What's the first term? 1, right? What's the second term? Nu. Why I am asking you this question is because it's so simple, okay, so that you are not lost in these things. So I want you to concentrate and just see that just sheer simple algebra and don't get carried away by these things. Nu divided by 1 minus nu, then 0 0 0. Is that clear? So, what does this indicate? This indicates that the shear strains have no effect on the tensile stresses, or rather not, I should not say tensile stresses, but normal stresses. Okay? They do not have any role to play as far as the shear strains, as far as they are concerned, they have no role to play. So, the second line starts with 1, that gets repeated, and yeah, and the third line starts with 1, 0, 0, 0, and all these things are symmetric terms. So, what is the fourth line? Rather, I think my lines are not very clear. Okay, let me write this separately. So that it's a big matrix, so that we know what it is. So, let us say that this is 1 nu divided by 1 minus nu, right? Nu divided by 1 minus nu, right? 0, 0, 0. Let me put that like this, right? And then 1 nu divided by 1 minus nu, 0, 0, 0, 1, 0, 0, 0. What is the fourth term? No, fourth term can't be 0 all the way, say. Yeah, here I have to fill it up here. Yes, all these things are 0, obviously, because first this 3, they are symmetric, so 3 are 0. So, there should be an entry in the diagonal term, obviously. So, what is that entry? 1 minus 2 nu, 1 minus 2 nu divided by, correct, 2 into 1 minus nu. Why? Because we have used gamma there. Is that clear? So, you have to be very careful. This is nothing, this is very simple, but you have to be careful. If you use epsilon, okay, correspondingly it will change that. So, do you get, say, now multiply this and that, E divided by 2 into 1 plus nu, which is G. So, you are correct. So, you will fill this up for the next 2 columns. Right. Have a close look at this equation now. Have a close look at this equation, this part of the equation. Can this equation, can this part of the equation, okay, can this spell, or can it spell some danger? Look at this equation. What is that? Nu, not gamma. Where is gamma here? Nu is equal to half. What is happening? What is happening? It becomes infinity. Okay? Yes. So, the material, do you think nu will be 0.5? No? Possible? Can it be minus? Can Poisson, see, these are some of the questions which you have to answer. Can nu be minus? Yes, what, tell me one material for which nu is equal to is minus. That means, what does minus mean? Please note this carefully. When nu is equal to minus, see, you look at way I defined it.
Which have been discovered recently.
Absolutely, there are certain forms which have been manipulated, okay, such that when you take this form and apply stress, instead of the other side coming in, the other side would start going up, going out. Okay, instead of coming in, it will start going out. When I pull a bar, okay, what will happen? The other sides would start coming in. Okay, then I defined nu to be positive, right? On the other hand, when I pull the bar, these sides start going out. What does it mean? Yes, absolutely, you are correct that there are certain forms which been discovered where the fellow will, instead of coming in, start going out, right? Now, but my question is, can nu be 0.5? Yes. Okay, for example, most rubber materials, where in fact you would have studied this, nu is equal to 0.5, there is one case where probably you would have studied, Where? Plasticity. For example, some of you would have studied, yes, correct. So nu is equal to 0.3 in the elastic region, and when material goes to plastic, you will say nu is equal to approximately 0.5. And in fact, many of you might have studied that rubber materials, nu is equal to 0.5. What does it indicate? That indicates that the material is incompressible. When nu is equal to 0.5, it can be shown that the material is incompressible, and it becomes very difficult to solve the problem using this multiplication of t. It is not possible because it will become infinite, right? Okay. Now, apart from that, there are a few things that we can look at from this equation. What is this? This is a general 3-dimensional equation. Okay. Now, the point is that should we use this kind of 3-dimensional equation all the time, or can I make a reasonable, meaningful engineering assumption to reduce this 3D into 2D? Or in other words, can I solve a problem as a 2-dimensional problem? Is that possible? In fact, the whole finite element modeling rests on concepts like that. They are, in fact, no doubt they are outside the view of finite elements per se, but in order to do a model, you should understand, you have to come to this extent to understand what is this. Okay. Now, if you wrongly write nu is equal to 0.5, then definitely you know that you are getting into trouble. That is why you should know this kind of equation, right? And there are special tricks of the trade that you will do in order to satisfy this constraint called incompressibility, right? But if time permits, we will come to that kind of tricks later in the course. Okay. And in fact, one more question I asked before we go to other simplification, well, can nu be above 0.5? Yes, unfortunately yes, in many codes even do not accept it. Many say reinforcements in tire, okay, some of the nylon reinforcements, they are believed to be above even 0.5. So many codes do not even accept it. There are problems from that point of view also. Okay, well, let us not worry about that, there are material aspects. Let us come back and look at whether we can simplify this 3D situation into 2D situation. Okay. Basically, there are 3 simplifications that are possible, and they go under the name plane strain, plane stress, and axisymmetric. Plane strain, plane stress, and axisymmetric. We will talk about this simplification in the next class.